Okay, this video is going to walk you through the document that Professor Miller made for Module 7. Okay, he starts with a topic that he's calling Introduction to Control, meaning that we've arrived at a certain point and now we have enough background material to actually start looking at how to design feedback control systems. All right, so in summary, you should have some and feel comfortable doing some modeling of systems. All right, so how to model systems: you write differential equations, you take the Laplace transforms, you look at transfer functions, you also look at block diagrams, so both transfer functions and block diagrams. And we use the Laplace transform to do much of our work. Okay, so by now that means you can represent the systems that we're trying to control. Remember, all models are wrong. Some models are useful. Sometimes the systems might be nonlinear, all right, but we're going to come up with a linearized model to try to make some progress on how to do control. So representing systems in the Laplace domain is an important step. Okay, from there, we're looking at reference inputs, and the most common reference input is, I think so far we've used the notation R of t as the reference input. So that means the Laplace transform is cap R, and if we're talking about a step function, the Laplace transform would be the amplitude of the step divided by S. Okay, just the Laplace transform of A U of t. Okay, so because we know about that, we can look at step responses for various systems. And when we say various systems, so far we've looked at first order. First order, you can't have any overshoot. It's just sort of an exponential growth up to a final value. And then there's also second order. And if you have a second order system with complex roots, then you get into the things like overshoot and settling time and those sorts of things. You can still have settling time and rise time in a first order system, and the book does cover that as well. Okay, so we're looking at how to characterize these things in both the time domain, because that's where we look at the step response, and then what does that mean in the Laplace domain? Typically we're looking at regions where the poles can fall so that you get the kind of response that you want. All right, so that's where we're heading. Let's move forward. So some of the objectives of coming up with a control system are that you want to meet certain properties that are deemed to be desirable to have. Okay, and so we get started with this list. The first thing on the list is stability. All right, so we've talked about that within this course, that if you have a stable system, if you have a bounded input, you should get a bounded output showing up. As you might imagine, if you put in a step into an unstable system and you get something that's either just continually ringing forever or shooting to either plus infinity or minus infinity, that's not going to work for us. So the system shouldn't grow without bound or oscillate without bound. Okay. The next thing that we've alluded to is tracking. All right, so you can define error because we have a feedback system. So you look at the error signal and you're trying to drive that to 0. So you have a reference input, you do that negative feedback, and you're trying to drive that to 0, but you might not ever get there completely, and so you can have something called the steady state error. All right, so hopefully we can track a reference input. When we look at the properties of a step response, how fast you track it, like rise time and settling time, all those things can be relevant for the application that you might have. Okay, next is regulation. Okay, typically a control system is going to have some things that you might call an external disturbance. All right, so for example, if you had a cruise control system and you encountered a hill, all right, so there's a disturbance because some of the dynamics would change because of the hill. All right, and so you'd want to be able to track that kind of disturbance. okay? And there also might be noise in the system. There's lots of ways that you can get some type of unwanted external disturbance. Okay, next is sensitivity. And sensitivity means that, typically if you have system parameters, like if you wrote some differential equations about the motion of a car, then the mass of the car is relevant. But, if you loaded up the car with a lot of passengers and luggage and stuff, the weight of the car would change, the mass of the car would change, and the dynamics change slightly because of that, and you'd still want your control system to work even if you had some system parameters that change. Okay, so those are the kind of things that we're starting to look at. So I'd like you to read this on stability and regulation and sensitivity, and also on tracking. Okay, so under the heading of tracking, we can go into a little more detail. So as I mentioned before, with a feedback control system, you form an error signal, which is the reference minus the output. You're trying to drive that to 0. You take the Laplace transform, you get R of S minus Y of S. Okay, so we talked about this in a previous video, that if you want to find the steady state error, then essentially what you're looking at is the final value, okay, so that'd be YSS, minus the reference value, if the reference, the steady state value of the reference, okay? I'm seeing a little bit of a, there's a little bit of a technical difficulty here because that implication of RSS is that RSS is a constant, all right? But you can have a ramp type of input, where the steady state solution is not finite, but it's tending towards a certain function. So, for example, a ramp, it would look something like this, all right? And if you had the output that was tracking it within a certain epsilon, that would still be tracking correctly as long as that error is not growing. Okay, so I don't want to falsely imply that you can only have a constant for the final value of the steady state value of the reference. Okay, so we can write these things in terms of the system transfer function. All right, so if you find the system transfer function, this would apply to either open loop or closed loop, as long as you get it to the form where you have R of S applying and out comes Y of S, applying to G of S and out comes Y of S. Okay, so from there, we talked about this a little bit in the previous video. You can apply the final value theorem, where the final value theorem says if you want the limit of the signal ESS as t goes to infinity, then you need to take the limit as s goes to 0 of s times E of S. All right, so plugging in the definition of the error signal reference minus output and multiplying by s, we have this s times R of S. All right, but remember, if we're looking at a step kind of a response, for example, R of S is A over S. All right, so that's what he's saying here. Apply a step of amplitude A, and you get R of S is equal to A over S. All right, you can do different reference signals, but this is what we're going to mainly concentrate on. All right, so from there, you get the transfer function, the S R of S cancels, and you get just the constant A. All right, and so when you take the limit as S goes to 0, you can use this formulation to calculate the steady state error. All right, so you should be able to do this with examples. Okay, one thing to know is that when you evaluate a transfer function at S equals 0, that's often called the DC gain. And the reason for that is, when you look at frequency responses, then what you're doing is you're plugging in S equals J omega, where omega is the frequency. Okay, so if you make omega equal 0, that would force S equal to 0, and you're evaluating this at the DC value. Okay, so this is the DC gain at frequency equals 0. All right, so we look at this and we literally plug in S equals 0, and you see all these terms just zap out to 0, all right, because you're plugging in S equals 0. So you're left with this limit of 10 over 15, which reduces down to 2/3. And so you can plug in, if you had, a step that's 6 U of S, okay, the 6 shows up here, 1 minus 2/3. We get a steady state error, in this case of 2, okay? All right, so if you're looking at open loop versus closed loop, the only difference in this is what is the final transfer function. Okay, so if you did a closed loop version of steady state error, then you need to look at the transfer function, and so we can get y over r equal to t, and t is given by this formula that I've told you several times now, that you need to recognize this pattern. Okay, and so this is the result that we used in the prior video where we were looking at steady state error for the homework in Module 6. All right, so in Module 6 we had the amplitude of the step being 1, so we found the steady state error would be 1 minus t of 0, and we found that the DC gain in Module 6 was 1, so the steady state error turned out to be 0. All right, that was a consequence of having an integral in the controller. Okay, we had that ki over s. That term is what drove the error to 0. Okay, so you can look through these examples. It's the same idea where you can use Laplace transform theory to calculate steady state error. All right, so hopefully that walkthrough helps. I urge you to spend a little time with this, read this, work on those calculations, make sure you understand them.